All right, folks, here we go. New chapter time. All right. So, chapter 10 for us now. This is static electricity. This is force. All right. So what you can kind of see is what the week looks like for this one and the next. Not too crazy as far as going forward with this stuff. Wednesday's video day, I'll show you exactly what that looks like so that you can take care of those videos over those next 3 days or so. All right. Quiz 10-1 is on next Wednesday and next Thursday, depending on hour, right? All right, here we go. Okay, so Unit 10 is about static electricity and electric fields. So for today, for what we're going to do is we're going to do basics of electricity or electric charge, properties of insulators, conductors, and charging objects. Okay. Your quiz next week will be on Coulomb's law and also on the basics here. All right. So I'm going to go ahead and kind of preface all of this stuff here before we start with, you've heard this before. Okay. So when we look at, properties of electric charge, here's what we're going to see. We're going to see that there are really three different types of charge. There's a positive, negative, and then no charge, right? Like charges repel, opposite charges attract. A proton is a positive one, an electron is a negative one. Now, again, none of this should be brand spanking new news to you. This all should be stuff that you're looking at and going, really, this is what we're teaching today? Yes, because this is how we started off this stuff. All right. So when we look at this concept of electric charges, charges are never created or destroyed, only transferred from one place to another. This becomes a big deal for us. Okay? Again, charges are conserved. When we look at this is conservation of energy, right? Energy is turned from GPE to KE. Yes, we may transfer it into friction, which is heat, but that's still just transferring it. Momentum is conserved, right? We're going around a corner, and momentum is going to continue to want to keep us going in that direction. All right. Charge is quantized, meaning it comes from specific little quantities, packets, or quanta, right? Quanta becomes kind of a nice word for us because that's how we start to describe these little groups of charges. All right. Fundamental unit of electric charge is a lowercase e, right? I know that seems weird, but that's the one that we use for that fundamental kind of beginning part of it. Charge of an electron is negative E. Charge of a proton is positive E. So it's 1.602 times 10 to the negative 19 coulombs. All right. So when we look at the charge of an electron, it's negative 1.602 times 10 to the negative 19. The charge of a proton, positive 1.602 times 10 to the negative 19. The charge of a neutron, 0 coulombs. Everything that has a charge has that as a whole number. So if all of a sudden we talk about having 6 electrons, that's 6e. That's 6 times negative 1.602 times 10 to the negative 19. All right. You cannot have half a charge. Again, when I taught chemistry for a very long time, the question became, okay, which part of the charge are you taking? The inside, the outside, the left, the right, the top, the bottom? Which one? All right. So again, for us, it has to be a specific amount of this, right? So conductors versus insulators. Now, hopefully you've seen conductors versus insulators. So when we talk about conductors, they are the metal bit in that wire up there. They allow charges to flow freely, all right? Metals tend to be really, really good at conducting stuff. All right. We tend to be pretty good at conducting stuff. Salt water is okay. Regular water, it's not great, but it's okay. Insulators don't allow charge to flow freely. Insulators, your plastic, your rubbers, some glass, some ceramic. These are actually going to block the flow of the charge. So if you look at that wire there, that's the plastic or the rubber bit on the outside of it, right? This is the stuff that when we pull out a plug, we want to be able to touch the insulators. We do not want to touch the conductors. In fact, it was in my college age years, I was working for the city of Chippewa Falls, Wisconsin, my hometown, and we were moving a old like oven range out of a outbuilding or something like that, and this thing was still plugged into 220. Now, if you don't know, the little outlet in the wall behind me, that runs 110. Okay? 220, that's the big stuff, right? If you ever look at your washer dryer, if you have electric ones of those are on 220s. All right. Some freezers in your garage, 220. All right. Anyway, so I was moving this and I was pulling on the top or on the plug of it. But what happened was is I couldn't get a good grip. So I wrapped my finger around the other side of the plug, and all of a sudden now my finger touched two of the three prongs on the 220. Now I know what you're thinking. Was this the time when I all of a sudden flew across the room? No, different time. But in this case, what happened was is that the conductor in that copper prongs of those 220 bits now allowed some electricity to start traveling. Where did I feel it? I felt it in my forearm. My forearm started to spasm, it started to tingle, and immediately I pulled my hand away and went, oh my gosh, so dumb of me. Grabbed the plug, pulled it out, nothing major happened. All right. Resistors are somewhere in between, allowing and not allowing. If you want to think of resistors, when you charge up your phones at night, the little brick or the little end piece that you plug into the wall, that is going to have resistors in it. Basically, what it's trying to do is it's trying to slow the charges down enough so that you don't get a straight dose of electricity to those sensitive components in your phone. If you were to do that, your phone would get fried. All right, which we don't want. Right. So, in checking these out now, whoops, sorry. The red here, this is a insulator. All right, it's a ceramic insulator on a power station. If you were to go over into Farmington or you were to go south of town on Lakeville, you would see major power stations like this where they have these kind of insulators so that you can kind of work around it. Now, the wire going in, the wire across the top here, excuse me, that's going to be the conductor, right? Those are those high wires. Those are the ones that, carry a pretty significant good amount of charge. All right. The conductor is full of electrons and protons. So in a conductor atom, the valence electrons are free to move about around an atom to atom. Now, I know we don't necessarily want to talk about valence electrons because that was a chemistry thing, but here again, we need to use the concept of these electrons as being free and able to move, right? They form somewhat of a Congo line for us. If you've ever known what a Congo line is, or you can think of just like you're waiting in line at the airport for spring break in a couple of weeks, right? Where all of a sudden you're just going to see these things just bumping into each other, just moving forward to forward, and they're just replacing one valence with the next valence, right? If you bring an external negative influence near it, the negative charges repel each other, and again, that's how our electricity will actually begin the process of flow, right? You plug it into the outlet, there is a external negative influence in there, meaning there's a lot of electricity in there. What happens is it just starts pushing down the line. It just starts to repel each other. These things start to get away, right? It's like if you have your own personal bubble and somebody steps inside your bubble, what are you going to do? I'm going to move, right? You get too close to me, I'm going to move. I don't know you, I'm going to move, right? If all of a sudden now you're a person that is messing with me and I know you, and then yeah, maybe we'll stay close. But really, I mean, that's really what it becomes is when you have your own personal bubble of space and somebody gets into that bubble and you're just like, awkward, this is weird, I don't like it, I'm gonna just start to move out of the way, right? So this is what we see here. We move that negative electron in, and what happens is that these start moving as vectors, and they start moving in a direction away from that. They're trying to get away. So what you see is this near one starts to move. This next one starts to move. This next one starts to move, and it just becomes a chain reaction of these things wanting, or of these electrons wanting to move. Now here again, if we plug something in with a copper wire, we're not going to get just one. We're going to get a steady stream of electricity running through that thing. Okay? All right. Now, so as we see it, it repels a nearby electron. That electron's neighbor finds it repulsive, and it moves away from them. And then they move away, creating a chain reaction that continues to have this happen. Now, it's going to move nearly at the speed of light. If you want to see this, take your light switch, turn it off and on. See if you can detect that difference when you flip it on. Right? Again, as soon as we flip that switch, what we're doing is we're allowing that negative external influence to now start to run through that wire. As it runs through that wire, what happens is our light bulbs end up experiencing that. As they get that run of electrons, that's going to allow them to either to charge the filament or to work through the LED or whatever you may have, the compact fluorescent. Okay. So valence electrons, again, the outermost in an atom. In conductors, these can move easily. Copper allows it to happen. Gold allows it to happen. Silver allows it to happen. Brass allows it to happen. Okay. Adding atoms of an insulating material hold on tightly to their valence electrons. They're locked into place so they don't move. That's the nice thing is that, and that's the reason why we want insulators. Okay. Is because that plastic, that rubber, that glass, right? What ends up happening is that we have all of these atoms locked, or these electrons locked in, so that when that negative influence hits it, it doesn't dislodge it. It doesn't move. It doesn't cause it to change places. All right. Now, again, this is a very simplified of what makes a metal conductor. All right. This is not the full story, but what ends up happening is this becomes a simplified description. All right. All right, charging objects. So friction. So when we do friction, we're actually scraping off electrons. So what you can see here in the GIF is that, dragging your feet across the ground, you're able to create a static charge. Now, is it big enough to create a shock like this? Not in any way, shape, or form. But you can create enough of a shock where you can actually startle somebody if you touch their earlobe or something like that, right? All right, conduction. What way do things flow? From low to high concentration or high to low? Objects are going to flow from high to low, right? So when we see a conduction piece, what ends up happening is that we have an area of high concentration. When it comes in contact, this area of high concentration now will lose that concentration. It'll spread out to an area of low concentration, right? If you ever use like those little Mio things or whatever they're called, the little drink boosters, right? If you drink those things straight, they are crazy concentrated, not very good, I think. Okay? But if you put it into water, what happens is it doesn't stay in that just kind of area that it is. What we now start to see is it spreads out. Right? If you've ever put food dye in water, same concept. Very concentrated bit of color goes in, and all of a sudden now it spreads out throughout that whole entire bit. Okay? So if we take a rubber stick, and we charge it up, and then we have a metal sphere with neutral charge, all right, as we bring that into contact, what's going to end up happening is those are going to spread all around it. Right? It's going to go from an area of high charge, where this bit is, to low charge, where that is, meaning that there's a high bit of negative charge on the metal sphere because we use friction to get it charged up. We touch it to the metal sphere. Now, guess what? It takes it and it adds to it. The sphere becomes negatively charged and the charge is spread evenly. Again, this is a model. We're not going to see all of this in the real world. Okay. In most real objects, the charges the positive portion of these, like the nuclei, don't move around. Okay. Here's an example. All right. What we start to see is we've got a negative, basically, you're like, I'll have to look it up. I can't remember it off the top of my head. It's right on the tip of my tongue. But basically, a charge hits the charge. All of a sudden, it becomes completely charged up. We move that away, and that becomes a possibly charged object. All right. I want to say like a Leyden jar or something like that. I think it is. Induction. The charged object never actually touches the object. This is the one that I call the little brother syndrome, right? Where if you've ever had that little brother who comes up to you and is like, touching you, I'm not touching you, I'm not touching you, I'm not touching you, right? They're doing induction. They're trying to be cute. They're trying to mess with you, okay? But it still influences the movement of the charge. No physical contact is made here, right? So when we see induction, what we're going to do is we're still going to bring that one close. But what happens here is these start to move. They get pushed away, all right? Now, here again, we're not going to rewire this metal sphere, meaning we're not going to take all of the positive nuclei and move them over here, and all the negatives are going to go over there. It becomes a theory, or it becomes a simplified version of it for us, in that, yes, those charges will want to get away because of that highly negative piece. Okay. So if the metal sphere is grounded, now this is kind of a crazy bit, right? If you put, like, I've had to replace light fixtures in my house. I've done a little bit of electricity work. I don't like doing it because it scares the hell out of me. But there's always a ground wire. The ground wire is the way for excess charge to get released, right? If you ever look at lightning bolts, like if you're driving through the country and you see a barn or something like that with a lightning bolt on the top, what you'll see is it has a wire that runs down to the ground. That's called a ground wire. So that if that lightning rod gets hit by, lightning bolt, then boom, it goes away from there and doesn't cause any damage, so to speak. All right. So if it's grounded, what this does is this gives it a way to get away, right? So what ends up happening is we start to see this thing now start to disappear and go out to the ground. Okay. It gives it a pathway to escape from, so to speak. Right. So what will then happen is our positive charges, after we move it away, will then redistribute. They'll spread back out. Well, kind of. Sorry, my animations aren't great. All right. But now we have a positively charged sphere for us. Okay. So same thing here. We take our negatively charged. It starts to push those away. They get to a ground. And so what happens is that the negatives leave. What we do is we create a positive charge here. All right. It becomes a nice little piece for us. All right. All right. So how does this work? Powder coating is actually something that's very interesting for us. When we powder coat something, what we're doing is we are basically dry painting. Okay. A dry powder is electrically statically applied to a surface, then that powder is cured. The process usually involves heating it until it melts, though there are other specialized processes, blah, 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 right? But basically what we have here is we're going to have a gun that's going to spray the paint onto this, right? Now, the reason why we say it's dry painting is because this is just going to be charged, all right? So it's going to be charged with all kinds of negative charges. But what happens is we ground that thing out. So all of the negative charges are allowed to go away. So what ends up happening is that this charged paint actually adheres and bonds to the object. When it does this, all right, what ends up happening is it forms a really, really good, solid structure. Okay? Advantage of powder coating over wet is that there are no solvents. That's what keeps the paint a liquid, smells funny as paint is drying. There's virtually no overspray. Excessive coating material that doesn't stick to the work and is unrecoverable. So basically what you end up seeing is the benefits are we don't overuse stuff here. All right. So, all right, another kind of example for it of you. All right. And here's what it ends up looking like. Okay. So what we end up seeing is that we're going to take this negative ions, right, of the paint basically, and they're going to stick to that, right? It says they're more positive than the charged powder, therefore the powder is attracted to the work spot. All right. You cook it then in an oven or something like that, and then what it does is it forms a very, very tight, almost, atomic level seal to it. All right. That's kind of the bit for the day. Hopefully this stuff makes a lot of sense for you and you feel comfortable with it. Okay. All right. Talk to you. Bye-bye.